Constant sum games and external regret minimization. A two-player constant sum game G equals to 1 to x1 s1 has the property that for some constant C, for every x1 in capital X1 and x2 in capital X2, we have S1 of x1 x2 plus S2 of x1 x2 equals to C. It is well known that any constant sum game has a well-defined value v1, v2 for the game, and the player I in either 1 or 2 makes the strategy which guarantees that its expected loss is at most v1 regardless of the other player's strategy. See Owen 1982 for more details. In such games, external regret minimization procedures provide the following guarantee. Theorem 4.9 let G be a constant sum game with a game value v1, v2 if a player I in either 1 or 2 plays for t steps using a procedure on with the external regret R, then its average loss 1 over t times L on to the t is at most vi plus R over t. Prove that Q be the mixed strategy corresponding to the observed frequencies of the actions player 2 has played. That is Qj equals to the summations of P2j to the t over capital T, summing for all those t starting from 1 to t, where P2j to the t is the weight player 2 gives to action j at time t. By the theory of constant sum games, for any mixed strategy Q of player 2, player 1 has some action xk in x1 such that the expectations of s1 of xk x2, if we assume that x2 is very similar to Q, then the expectation of such thing is less than equals to v1, see Owen 1982. This implies, in our setting, that if player 1 has always played action xk, then its loss would be at most v1 times t. Therefore, L mean to the t is less than equals to Lk to the t less than equals to v1 times t. Now, using the fact that player 1 is playing a procedure on with the external regret R, we have that L on to the t is less than equals to L mean to the t plus R, which is less than equals to v1 times t plus R. Thus, using a procedure with regret R equals to big O of square root of t times log n as in theorem 4.6 will guarantee average loss at most v1 plus big O of square root of log n over t. In fact, we can use the existence of external regret minimization algorithms to prove the minimax theorem of a two-player zero-sum games. For player 1, let v mean to the 1 equals to min max, where min is for taking all those x1 in capital X1, and the max is for taking all those z in delta of capital X2 for the expectations of s1 of x1, x2. If we assume that x2 is very similar to z and the v max to the 1 equals to max mean, another max mean, for the max is taking all those x2 in capital X2, and the mean is for all those z taking in delta of capital X1 of the expectations of S1 of x1, x2, if you assume that x1 is very similar to z. That is, v mean to the 1 is the best loss that player 1 can guarantee for itself if it is told that the mixed action of player 2 in advance. Similarly, v max to the 1 is the best loss that player 1 can guarantee to itself if it has to go first in selecting a mixed action, and player 2's action may then depend on it. The minimax theorem states that v mean to the 1 equals to v max to the 1, since s1 of x1, x2 equals to minus s2 of x1, x2. We can similarly define v mean to the 2 equals to minus v mean to the 1, and v max to the 2 equals to minus v mean to the 1. In the following, we give a proof of the minimax theorem based on the existence of external regret algorithms. assume for a contradiction that V max to the 1 equals to V min to the 1 plus gamma for some gamma which is greater than 0. It is easy to see that V min to the 1 is greater than or equals to V min to the 1. Consider both players playing a regret minimization algorithm for t steps, having external regret of at most r such that r over t is less than gamma over 2. Let L on be the loss of player 1 and note that minus L on is the loss of player 2. Let L min to the I be the cumulative loss of the best action of player I chosen from either 1 or 2. As before, let Qi be the mixed strategy corresponding to the observed frequencies of actions of player I chosen in 1 or 2. Then L min to the 1 over t is less than or equals to V min to the 1. Since L min to the 1, we select the best action with respect to a specific mixed action, namely Q2. Similarly, L min to the 2 over t is less than or equals to V min to the 2. The regret minimization algorithms guarantee for player 1 that L on is less than or equals to L min to the 1 plus R, and for player 2 that minus L on less than or equals to L min to the 2 plus R. Combining the inequalities we have, t times V max to the 1 minus R is equals to minus t times V max to the 2 minus R, which is less than or equals to minus L min to the 2 minus R, which is less than or equals to L on, which is less than or equals to L min to the 1 plus R, which is less than or equals to T times V min to the 1 plus R. So this implies that V max to the 1 minus V min to the 1 is less than or equals to 2 times R over t, which is less than gamma, which is a contradiction. Therefore, V max to the 1 equals to V min to the 1, which establishes the minimax theorem.